Hello, and welcome back to Thermo. I'm posting these videos on probability out more as kind of a cultural thing, so you can get a sense for how to work with probabilities and just sort of it's the type of thing that you're supposed to kind of know, but no one ever sort of tells you. Um, so it fits into thermodynamics because when we want to treat large collections of particles, we have to treat them statistically. And so that's where the concept of probability and statistics will enter. But really, while we're here, I'm going to put in some extra stuff that maybe we won't need, but it's not going to hurt you to know. So we'll have a couple videos on this, I think. Um, I won't be testing you on this material. It's more kind of for completeness, so you have an overall sense of things. So I want you to imagine a situation where, excuse me, um, assume you're told that there's a class of 28 students, I'm reading the numbers here so I get it right, and the average score on the exam was 75%. And is that enough for you to characterize how the class performed? Well, probably not, because there are many ways you could imagine everyone scoring 75 or having an average of 75%. Maybe everyone scored 75%. Maybe half the people scored 50% and half the people scored 100%. Either, both of those scenarios would amount would give rise to an average of 75%. So um, what we would prefer to have maybe is a little bit more information. We would want to know maybe for all the possible scores, how many students achieved each score. So and we could arrange that maybe in a histogram sort of fashion. So if I made a graph, oh, here, and let me we're going to say that Ni equals the number of students scoring I. And I'm going to quote this as a percent. So, and we'll just assume it wasn't too bad. So nobody got less than 50. So 50, 60, 70, 80, 90, 100. Okay. And let's assume that, okay, so we'll do 2 there. And we'll say, oh, let's just say this would be, so on the vertical axis, I'm going to have n sub I, and this is 2, 5, or 7. So maybe I look at my outcomes and I plot out and I see that, oh, um, 2 people scored 50%, and let's say 5 people scored 60%. Okay, and then let's assume that perhaps 7 people scored 70, maybe another 7 scored 80, and then back down to 5 scoring 90, and then maybe 2 scored 100. Okay, so and I should also tell you because I'm imagining exam scores or something real, some experiment really that's being done. This would be called an experimental probability, as opposed to sort of a abstract one, like throwing a coin where we'd say half go one way, half go the other. I say that without actually having done 14 million coin tosses. It's an abstract or theoretical probability. Okay. So let's check that out. Notice, first of all, notice, note, if we were to add up the number of students who achieved each possible score, so adding up all of the times each score was achieved, well, everybody scored something, so that better add up to the number of students. So I could say that could be like the number of students. Okay, so let's go through that. So in this case, that would be 2 plus 5 plus 5, oh, plus 7 plus 7 plus 5 plus 2. I'm just adding up 2 plus 5 plus 7 plus 7 plus 5 plus 2. And those give me, let's see, 7, 4 times 7 is 28. Okay. So when you add up all of the times each result was achieved, well, that's all the possible trials basically that have been attempted. So that should add to the number of students. And then the other thing you can do is you can divide the number of times each score was achieved divided by the total number of times some score was achieved, which would be the number of students. And so this would tell you what fraction or percent of the time each separate score, I, was achieved. So this is the in other words, this would be our experimental estimate for the probability that score I was achieved. The probability of scoring I on the test. Let's think about that. What do probabilities, let's just try to justify that a little bit. Probabilities cannot be negative, so this is a check. Probabilities must be negative, or must be positive or 0, so non-negative. Well, okay, these fractions are all non-negative. And furthermore, when you add up all possible outcomes, the total probability will be 1, because you're basically saying something had to happen. So let's check that. So I should have that the sum of all the probabilities summed over each outcome should equal 1. So let's check here. Well, the first one is obviously true. The second one, well, let's go through that. I'm going to use this formula here. So I'm going to have sum on pi over all I, so sum over number of I over the number of students. And this denominator is just a constant factor, so it actually pulls outside. But if you flip back at one page, you'll see that the sum just equaled the number of students. So the sum is the number of students. And in fact, this equals 1. Check. Because the denominator cancels the numerator. All right. So these it's at least plausible that these could be a probability because they satisfy the correct um, kind of rules for probabilities. They can't be negative and they have to add up to 1. Now, we would assume if you do one exam, then that experimental probability, I mean, it's just that, you don't know that if it's going to carry forward. You really should have more and more and more and more trials and keep better and better, um, and keep all the records. And what you will hope is that the the outcomes will settle down into a kind of more. So I guess what I'm saying is the size of the deviations from the probability, from the kind of average probability distribution, will shrink in relative size to the overall number of samples you've taken or made. Okay, so in general, then we're just going to do the same thing. So the idea is going to be if we have an outcome I, we'll just call it I, occurring n sub I times, and with in total trials or attempts or experiments or data points, doesn't matter, but various just events, then we will have that the probability of outcome I equals the number of times I was achieved over the total number of attempts made. And just as before, you can show that this will satisfy the axioms needed to be a probability. Awesome. So now, how do we use this? Well, we're going to define a couple ideas. The first is like an average or expectation value. Or mean value. And I'm being a little bit sloppy with some of the language. The example I gave before was for a discrete set. And so the average and mean are slightly different than the expectation value. Whereas when things are continuous, they are the same. It doesn't matter for us. Okay, you get the idea. So I will just call them expectation value or mean value. And the way I would write this, I'm going to say that the mean value of some quantity. So let's say I had some outcome, some something I wanted to measure, some f, and f is some function of the result or the score I. Okay, so f is some attribute, and it depends upon what score was achieved on a test, or it could be anything, but on some other. Well, we're going to call these random variables. These things that we look at a distribution of. And so if I want to know the average outcome for f, sometimes people write that or this for average. I tend to like that just because that's how it looks in quantum mechanics when people write it. So this is the average. Okay, so average, or sometimes I put this bracket around it. So I would say that the average value of f, and this is really a definition of what I mean, is defined to be, and what you do is you sum over all possible outcomes, sum over all possible values of the random variable I, and you evaluate the function on this on this, and you multiply by the probability that I was achieved. So basically, it's kind of like, well, you know, think about averages in high school. You kind of added up all the contributions, and you divided by the number of things you added. Well, that's kind of what's happening here. You're adding up all the number of outcomes, and you're not dividing by the number of outcomes, but you're multiplying by the probability that each one was achieved. I'll give an example here, and kind of connecting these. All right, so this is the average value. Let's go back. You know what? I tell you what, we're going to do two examples here for average value. One is just a simple average value like you would do in high school or grade school. And then we'll also go through and kind of apply it to this data set. And then we'll stop the video. And we'll pick it up next time. All right, so let's do an example. Let's say that we have okay, let's assume we have a die, 6 faces. They're all equally likely. Okay, so how many outcomes are there? How many ways could I roll this and get something? Well, there are 6. So so what I'm going to get is that the probability of getting each face. So all right, let's read that. I labels the side or the face value. So that'd be 1 to 6. And if we were to roll this over and over and over and over and over, many times, assuming it's not a loaded die, what you would expect is many times it would hit each number, but the number of total rolls would be even larger. In fact, we would expect that 1/6 of the time it would hit each face. So we'll assume that that's right. So the probability of rolling each face is the same. It's all going to be 1/6 because it's not a loaded die. All right. And we can check if you add, so check that sum over I from 1 to 6 of Pi, that's just a 6 plus 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 a 6. I think I got them all. Anyways, that's 1. Does that make sense? And I could say, okay, what is the average value? So if I was to roll this many times, what would be the average value I would expect? So I would take, the formula would say the average value for I, the side that would turn up. So what would be the average? Maybe I'll write this differently. Maybe I'll say the average value for the side. Well, you know, half the time it's 3 or below, half the time it's 4 or above. So the average is going to be right down in the middle. It's going to be 3.5. Let's see how that works out. So the formula for an expectation value or average is, so in this case, I'm going to have f of I is just I itself, just the value of the side, 1, 2, 3, 4, 5, 6. And so my formula is to take, I want to sum over all possible outcomes, the value, I'll write it out here, f of I times the probability of I, which in this case becomes the sum from I equals 1 to 6, I times the probability, and they're all the same, 1/6. Sorry. Well, that's just 1/6 times the sum over I from I equals 1 to 6. Now, I don't know if you remember this, but this is a known formula you should have seen in pre-calc. So it is going to be 6 times 6 plus 1 over 2 multiplied by 1/6. So that's going to be 6 times 6, sorry, 1/6 from the probability times 6 times 6 plus 1 is 7 over 2 equals 3.5. Okay, so the answer we get is the average value is 3.5, which is what I said it should be. All right, so that's how you can use probabilities to find the average value. Now, look what happens. When you have a flat distribution or a uniform probability, then really you just add up the number of all the outcomes, the result of all the outcomes, you just divide by the number of times you got anything, and that gives you the average. This is just what you would have calculated in high school. It may not look like it, but that's what you would have done in high school, where the dividing by the number of attempts, that's the same as multiplying by the probability. So that's how it connects. The average, this notion of average connects to what you've learned before. Let's go to the example I started with. I had these as my outcomes. Okay, so in that situation, I'd have Ni, Pi, and my in total was 28. So in I, oh, and here I had I. So when I had 50, my in number of times people scored 50% was 2. The probability of getting 50 would be 2 over 28, or 1 over 14. Then I had 60, which occurred 5 times. The probability would be 5 over 28. And 70 occurred 7 times, which shows the probability to be 7 over 28, 1 over 4. Sorry, 1 over, yeah. And then I had 80, which occurred 7 times, which was 7 over 28, which is 1 over 4. And 90 was 5, so that's going to be 5 over 28. And 100 occurred twice, so the probability is 1 over 14. Okay, so those are my probabilities for my outcomes. And if I want to know what is the average score, well, the score is just the value of I. So I use my formula for the average value, and I would say that is the sum from I equals 50 to 100. All the others have 0 probability. And I would say it would be the score I times the probability of achieving score I. And if you go through that, the answer you get, well, let's just write down how that would go. So that would be 50 times 1/14 plus 60 times 5 over 28 plus, sorry, these are tedious, 70 times 1 over 4 plus 80 times 1 over 4 plus 90 times 5 over 28 plus 100 times 2, or 1 over 14. Now, if you type all that in, you in fact get exactly 75. So we would learn that the average value of the score is is 75. And that makes sense, because if you look at that probability distribution, or you look at those outcomes, you see, I mean, this is on some sort of a curve, right? But the average would be right down the middle because it's symmetric, and that's at 75. So that's a reasonable outcome. Okay, All right, so that's how you find average values of things given a probability distribution. All right, I'm going to stop the video there. Next time we're going to talk about standard deviation, which has to do with the average distance away from the average. So how noisy things are. And then we'll have some examples using calculus to do the same thing. Okay, so catch you next time.